Hello, everyone. Good morning or good evening, wherever you are, or good afternoon. Today is another day of learning, continuing my morning study of Kubernetes. Yesterday, we looked at the cluster components at a simple and basic level. Today, I am now going deeper, okay, into the cluster components. So if you had your notes, like I have mine here, yesterday we looked at the control plane and also we looked at the node. Okay, so the cluster components at a basic level has a control plane, and then we also have what is called the node. So you can have one or more nodes. Okay, so we learned that the control plane has things like the scheduler, it has things like the API server. We had those kind of tools. Okay, we had like the etcd, which is for the a key value store. Okay, and in addition to that, we had the node, which has things like the container runtime. Okay, so let's get into them. Of course, I may not have to. You may not have to remember everything off the top of your head, but the more we do this, the more it will stick in our minds. Okay, like right now, I've just remembered one thing called the kube control manager. Okay, then there's also the cloud control manager, which is actually optional. So yeah, we'll keep, and actually today the cluster architecture, when you see this topic, it's going to go a little bit deeper into each concept, into each architecture concept. Now I know I've begun 30 minutes late from the time we've been studying since the past 2 days, and I'm sorry for that, because I prefer doing it in a consistent time base so that even you who's watching, you know that it's consistent. Okay, so let's go ahead. Cluster architecture. So it says the architecture concepts behind Kubernetes. It says a Kubernetes cluster consists of a control plane plus a set of worker machines. We saw this yesterday. And it says these worker machines are called nodes. Remember, I speculated what nodes are yesterday, and it turns out I'm actually right. So it says that, let's read this again. A Kubernetes cluster consists of a control plane plus a set of worker machines called nodes that run containerized applications. Every cluster needs at least one worker node in order to run pods. Okay, so in other words, every cluster needs at least one machine. So every time they talk about a node, in my mind, I'll just know that that is the machine. Okay, every cluster needs at least one machine to run pods. That should make sense, because how would you have a cluster without a machine? Okay, no machine equals no cluster. No machine means no orchestration of your container happening. Okay, and like we saw yesterday, a cluster has at least one node. Okay, those nodes have pods, and those pods are the ones that have container runtimes, which run the containers for us. All right, let's go ahead. This says the worker nodes host the pods that are the components of the application workload. The worker nodes host the pods that are components of the application workload. The control plane manages the worker nodes and the pods in the cluster. Okay, so again, the node is simply machine, and this machine hosts the pods. Okay, which are the components of the application itself. Okay, and like we learned yesterday, that the control plane is used for managing those nodes and pods in the cluster. So they're saying in production environments, the control plane usually runs across multiple computers, and a cluster usually runs multiple nodes, providing fault tolerance and high availability. I want to read this again. They're saying in production environments, the control plane usually runs multiple computers, and a cluster usually runs multiple nodes. So control plane manages multiple computers, and a cluster runs multiple nodes or machines, providing fault tolerance and high availability, so that in case maybe one node goes down, the others which are available, okay, can pick up and continue providing the business solutions to the clients. Okay, next up, they're saying this document outlines the various components you need to have for a complete and working Kubernetes cluster. Okay, so we see a diagram here. I'm not sure if you can see it well. The more I zoom in, the smaller it becomes. Okay, but it simply it's illustrating the Kubernetes cluster. Okay, this is the control plane. Okay, this is the entire cluster. Then we have the control plane. Like we say, it's the cloud control manager, which helps us to configure things on the cloud. We have the Kube-Apiserver, which exposes an HTTP API server. Okay, we have the etcd, we have the kube scheduler, which is responsible for. We have the control manager. Okay, don't confuse between the control manager and the cloud control manager. Control manager always ensures that we reach the desired state. Okay, and the scheduler, like we saw, is responsible for ensuring that the nodes have what is supposed to be in them, okay, to be run and have the right configuration. Then we see the nodes, which has a kubelet, which is responsible for managing the nodes. Kube-Proxy, responsible for managing what? Networking roles. Yeah, but let's go ahead, okay, because this is faint, you may not see it properly. Let's read this, okay. So this is now more detailed what we studied yesterday. So let's say control plane components. It says the control plane's components make global decisions about the cluster. For example, scheduling, as well as detecting and responding to cluster events. For example, starting up a new pod when a deployment replicas field is unsatisfied. Okay, so what I get from this is that the control plane helps us with scheduling. Why? We see that it has the scheduler. Okay, we see that it's responsible for setting up a new pod. Okay, so it can detect that we need a new pod, and it will start up a new pod. Okay, so this says a pod can be started when the replicas copies of pods, okay, and are not satisfied. Okay, so here when I hover over this, it says replicas are copies of pods, ensuring availability, scalability, and fault tolerance by maintaining identical instances. Okay, so in case maybe we need 5 replicas and then 1 replica goes down, the control plane ensures that we have those 5. Okay, now they're saying control plane components can be run on any machine in the cluster. However, for simplicity, setup scripts typically start all control plane components on the same machine and do not run user containers on this machine. They're saying see highly available clusters with kube-dem. For example, for an example control plane setup that runs across multiple machines. And I don't want to divert away from this, okay? Maybe there's something we can look at later. For now, I want to focus on the architecture, okay? So I will move on to the next topic, which is the Kube-Apiserver. So again, it's what we studied yesterday, but on a much deeper level. So they're saying the API server is a component of the Kubernetes control plane that exposes the Kubernetes API. The API server is the front end for the Kubernetes control plane. Yeah, saying it's the front end for the Kubernetes control plane is a much more good explanation. Okay, and I like that they have done this because it's better than what we studied yesterday. Okay, so let's move on. Now they say the main implementation of a Kubernetes API server is Kube-Apiserver. Okay, and then they say Kube-Apiserver is designed to scale horizontally. That is, it scales by deploying more instances. This is actually the entire definition of horizontal scaling. Okay, you create more instances of something. And then they're saying you can run several instances of Kube API server and balance traffic between those instances. So in other words, they're saying for this Kube API server, we can have multiple frontends, okay? Multiple frontends for our control plane, okay? And we can say some requests to this frontend of our control plane goes maybe is the traffic, okay? Or the request to this control plane can be shared between maybe 4, okay? Between 4 API servers. Why? To help us balance traffic, because maybe one API server may not be able to handle traffic, okay? So we split it across a number of instances, okay? So instead of maybe one API server, we have 4 API servers so that traffic is balanced and shared between these 4 instances or copies, okay? Yeah, but I like this. Now we're just going deeper into what we learned yesterday. Then we have etc, the etcd. If you remember, this is the key value store. Now, do not get tired of reading the same things again and again. In fact, I love doing this because this is how you achieve mastery. Okay, the way to master is by doing something over and over again. So let's go on. The saying, consistent and highly available key value store used as Kubernetes backing store for all cluster data. So again, if you've not watched day 1 and day 2, please go back and watch them because this is a series, okay? And if you're enjoying this, then you watch maybe when it's recorded, yeah, share it in your community so that we have more people learning with us. So it's saying a consistent and highly available key value store used as Kubernetes backing store for all cluster data. We saw this yesterday. And they go on to say if your Kubernetes cluster uses etcd as its backing store, make sure you have a backup plan for the data. Okay, so this is storage for all the cluster data. So we have to make sure you have a backup plan. Okay, this is, I think, what we should do. That is the etcd that's in a database. Okay, file storage we must always have. We must always have a backup plan. So they're saying you can find an in-depth information about etcd in the official documentation. Okay, of course, yeah, for now we don't need that. Okay, let's go ahead. They're saying now we're going to the kube scheduler. Okay, so they're saying the control plane component that watches for newly created pods with no assigned node and selects a node for them to run on. Okay, yeah, this is a good reminder. The scheduler simply looks at the cluster and says, okay, where are pods which have been created, okay, that don't have a machine to run on. So remember, a node is simply a machine, okay? So it gets the pod and assigns it to, gets a pod and assigns it to a node so that the pod has a machine to run on, because a pod cannot run without a machine. Then they say factors taken into account for scheduling decisions include, they say, individual and collective resource requirements, hardware, software, policy. Okay, let me read this again. Individual and collective resource requirements, hardware or software or policy constraints, affinity and anti-affinity specifications, data locality, inter-workload interference, and deadlines. What's affinity? Okay, I don't know what they mean by this. Let me just drop this in Google and see if I can get a quick explanation. They're saying affinity and anti-affinity specifications are directives typically in cloud-native environments like Kubernetes that influence the scheduling of workloads like pods to ensure they are placed on specific nodes or other workloads for reasons of performance, resource optimization, or availability. So it is simply like the directives like a rule, okay? That can I say in simple terms, I think it's like configuration, okay? For lack of words, like configuration that tells the scheduler what pods and what nodes, okay, are available and what new pod to assign to each node. That's how I get it. Then, Of course, if you've understood this better, feel free to leave a comment. Then we have the Kube Control Manager. They say this is the control plane component that runs controller processes. And if I hover over this, they're saying a controller is simply a control loop that watches the shared state of the cluster through the API server and makes changes, attempting to move the current state towards the desired state. So yeah, we saw this yesterday. So the controller processes simply watch the whole cluster using the API server, okay, to be able to know, okay, that the current state, okay, our desired state. If it's not, then it moves the whole setup towards the current state. And that is by doing things like assigning a new pod to a node. Then you're saying logically each controller is a separate process, but to reduce complexity, they are all compiled into a single binary and run in a single process. Okay, this is good to know. I wonder how they would implement this. I think sometime I would want to go into this kind of low level engineering. Okay, they're saying there are many different types of controllers. Some examples of them are, they have the node controller. Okay, this is good. They didn't talk about these controllers. Okay, node controller is responsible for noticing and responding when nodes go down. Excuse me. So the node controller is responsible for noticing and responding when nodes go down. Then we have the job controller, which watches for job objects that represent one of tasks, then creates pods to run those tasks to know completion. Endpoint slice controller populates endpoint slice object to provide a link between services and pods. Service account controller created default service accounts for new namespaces. I don't think I need to cram all these. Okay, what I need to know is just to know what a controller is, okay, and what it does. If I need maybe a specific niche function, yeah. In fact, even in an interview, I would admit that I don't have all this by memory, but at least I know what a controller does, what they call what the single process, okay, called the Kube Control Manager does. And of course, the documentation is there for us to figure out what particular type of controller I need to use. So saying this is not an exhaustive list, meaning the others, okay? I'll go to the Cloud Control Manager, okay? So they're saying a Kubernetes control plane component that embeds cloud-specific control logic. The Cloud Control Manager lets you link your cluster into your cloud provider's API and separates out the components that interact with that cloud platform from components that only interact with your cluster. Okay, separates out the components that interact with. Let me read this again. The Cloud Control Manager lets you link your cluster with your cloud provider's API and separates out the components that interact with the cloud platform from components that only interact with your cluster. Simply integrating with the cloud provider like AWS, GCP, whatever, okay? And has some separation of concerns that what interacts with the cloud platform like AWS is separate from what interacts with our cluster, okay? Next, they're saying the Cloud Control Manager only runs controllers that are specific to your cloud provider. If you're running Kubernetes on your own premises or in a learning environment inside your own PC, the cluster does not have a Cloud Control Manager. So like on my machine, I will not have a Cloud Control Manager, okay? It only runs controllers which are specific to the provider. Okay, so let's go ahead. So it's saying, as with the Kube Control Manager, the Cloud Control Manager combines several logically independent control loops into a single binary that you run as a single process, okay? You can scale horizontally, which means you can run more than one copy to improve performance or to help tolerate failures. Next up, is saying the following controllers can have cloud provider dependencies. They have the node controller, which they're saying for checking the cloud provider to determine if a node has been deleted in the cloud after it stops responding. We have a route controller, which is responsible for setting up routes in the underlying cloud infrastructure. Then there's a service controller, which is for creating, updating, and deleting cloud provider load balancers. Okay, then so that's all for the control plane. Yeah, so control plane has the etcd, the Kube control manager, the Kube cloud control manager, the Kube API server. Okay, yeah, it's now getting easier to understand. The Kube API server, which is simply the front end, which simply exposes an HTTP API, okay, for interaction. Then the etcd, which is the storage, the key value store, the scheduler, which is responsible for assigning new pods to nodes, the control manager, which is responsible for watching over the whole state via the API server and ensuring that the whole state, the current state, which is the desired state. We have the cloud control manager, which is for integration with cloud providers, APIs. Then now we're on node components. So node components, they say node components run on every node, maintaining, running pods, and providing Kubernetes runtime environment. Okay, let me read this again. Node components run on every node, maintaining, running pods, and providing the Kubernetes runtime environment. So we have the kubelet. Okay, the kubelet is an agent that runs on each node in the cluster. It makes sure that containers are running in a pod. Okay, so simply a software way to a process that ensures that containers are running in a pod. Okay, then I'll come here to the next statement, which says, so the next paragraph, which says, the kubelet takes a set of pod specs that are provided through various mechanisms and ensures that containers described in those pod specs are running and healthy. Okay, ensures that the containers described in those pod specs are running and are healthy. It says the kubelet doesn't manage containers which are not created by Kubernetes. Okay, this is interesting to know. Then we have the Kube-Proxy, which is optional. They're saying Kube-Proxy is a network proxy that runs on each node in your cluster, implementing part of the Kubernetes service concept. Okay, and they're saying Kube-Proxy maintains network rules on nodes. These network rules allow network communication to your pods from network sessions inside and outside your cluster. Okay, I want to read this again. Kube-Proxy is a network proxy that runs on each node in your cluster, implementing part of the Kubernetes service concept. Okay, so they're saying this Kube-Proxy maintains network rules on nodes. These network rules allow network communication to your pods, network sessions inside and outside you. Simply enabling communication. Okay. So they're saying Kube-Proxy uses the operating system packet filtering layer if there is one and it's available. Otherwise, Kube-Proxy forwards the traffic itself. If you use a network plugin that implements packet forwarding for services by itself and providing equivalent behavior to Kube-Proxy, then you do not need to run Kube-Proxy nodes in your cluster. Okay. So if we have a network plugin that implements forwarding, okay, that helps us like between communication between our pods, okay, from network sessions inside and outside of our cluster, then we don't need Kube-Proxy. I think that's why actually say it is optional. So the next one is the container runtime. They're saying it's a fundamental component that empowers Kubernetes to run containers effectively. It is responsible for managing the execution and lifecycle of containers within the Kubernetes environment. A fundamental component that empowers Kubernetes to run containers effectively. It is responsible for managing the execution and lifecycle of containers within the Kubernetes environment. Okay, so like we know that Kubernetes is a container orchestrator. So at the very, very, very bottom, okay, would expect that they have something responsible for running the containers. So this makes sense. Okay, container runtime help us run the containers that Kubernetes is going to help us to orchestrate, because Kubernetes is simply a container orchestration platform. So at the end, you expect to have a runtime. The next paragraph says Kubernetes supports container runtimes such as containerd, okay, CRIO, and any other implementation of Kubernetes CRI, okay. So CRI is container runtime interface. If I hover over this, they say containerd is a container runtime with an emphasis on simplicity, robustness, and portability. What is CRIO? They're saying it's a lightweight container runtime specifically for Kubernetes. Then, like we saw yesterday, now they are talking about add-ons. So let us look about some of these add-ons. We're almost done with this, okay? So for the add-ons, we have the saying Kubernetes uses resources, okay, like the daemon set, deployment, etc., to implement cluster features. Because these are providing cluster level features, namespace D resources for add-ons belong with the kube system namespace. The saying selected add-ons are described below. For an extended list of available add-ons, please see add-ons. Of course, now we don't have to cram this, okay? Like I always tell you, there's no need to cram this. But it's good to be just slightly aware of something so that when you need it, you always come the documentation, okay? Now, at least, even if I stopped here, I know that Kubernetes has add-ons, okay? So in case I wanted to do something, I would look up the add-on that can do what I need, okay? Maybe you can hover over this to see what daemon set means. The saying ensures a copy of a pod is running across a set of nodes in a cluster. Okay, deployment. This manages a replicated application on your cluster. Okay, let's look at the add-ons one by one. Okay, so DNS, like we looked at yesterday. Okay, by now, if you're a developer who has been writing code for some time, whether front end or back end or mobile, you should know what DNS is. Or if you've ever bought a domain, okay, and hosted an application, you know what DNS is all about. So they say while the other add-ons are not strictly required, all Kubernetes clusters should have cluster DNS, as many examples rely on it. Okay. They're saying cluster DNS is a DNS server in addition to the other DNS servers in your environment, which serves DNS records for Kubernetes services. Containers started by Kubernetes automatically include this DNS server in their DNS service searches. Okay. Let's go to the next one. We have the web UI. But I feel like I need to read this again. It looks a bit deeper than what we had yesterday. It's saying while other add-ons are not strictly required, all Kubernetes clusters should have cluster DNS, as many examples rely on it. Okay. So we need a cluster DNS. This is what I get from that. And they're saying a cluster DNS is a DNS server in addition to the other DNS servers in your environment, which serves DNS records for Kubernetes services, okay? The goal here is to simply provide DNS records, okay? And they're saying clusters started by Kubernetes automatically include this DNS server in their DNS searches, okay? So it is added for us. Then we have the web UI dashboard. They're saying dashboard is a general purpose web UI for Kubernetes clusters. It allows users to manage and troubleshoot applications running in the cluster, as well as the cluster itself. When I move on here to cluster resource monitoring, they're saying cluster resource monitoring records generic time series metrics. Okay, cluster resource monitoring records general time series metrics about containers in a central database and provides a UI for browsing that data. Then we have now cluster level logging. They're saying a cluster level logging mechanism is responsible for saving container logs to a central log store with a search or browsing interface. Okay. Next up, we have network. Actually, logging, yeah, modern logging, yeah, things we always need. Network plugins are software components that implement the container network interface CNI specification. What is CNI? Okay. I think CNI is the abbreviation for container network interface. The C for container, the N for network, the I for interface. And they're saying they are responsible for allocating IP addresses to pods and enabling them to communicate with each other within the cluster. That makes sense. To communicate, every pod must have an IP address. Then we have architectural variations. They're saying while the core components of Kubernetes remain consistent, the way they are deployed and managed can vary. Understanding this variation is crucial for designing and maintaining Kubernetes clusters that meet specific operational needs. Okay, I'll go on. It's a control plane deployment option. So the control plane can be deployed in several ways. They're saying traditional deployment. So the control plane components run directly on dedicated machines or virtual machines, often managed as systemd services. Okay, that's the traditional way. Okay. Then they're saying static pod. They're saying the control plane components are deployed as static pods managed by the kubelet on specific nodes. This common approach is used by tools like Kube-apiserver. Okay, so here the traditional they manage as systemd services. Here they're managed, okay, by the kubelet. Then I go self-hosted. So the control plane runs as pods within the Kubernetes cluster itself, managed by deployment and stateful sets or other Kubernetes primitives. They say manage Kubernetes services. They say these are cloud providers often abstract away the control plane, managing its components as part of their service offering. Okay, interesting. Okay, we are almost there. So work placement considerations. They're saying the placement of workloads, including the control plane components, can vary based on cluster size, performance requirements, and operational policies. In smaller or development clusters, control plane components and user workloads might run on the same nodes. So they're saying larger production clusters often dictate specific nodes to control plane components, separating them from user workloads. Okay, so there's a separation between control plane components and user workloads. And I think some organizations run critical add-ons or monitoring tools on control plane nodes. Okay, done with that. So when we look at cluster management tools, they're saying tools like, is it Kube-apiserver, okay, Kops and Kube-Spray offer different approaches to deploying and managing clusters, each with its own method of component, layout, and management. Of course, if I'm pronouncing these things wrongly, don't hesitate to correct me. The flexibility of Kubernetes architecture allows organizations to tailor their clusters to specific needs, balancing factors such as operational complexity, performance, and management overhead. So the goal is just simply to help us understand that we can tweak the setup, okay, according to our needs. So customization and extensibility. The same Kubernetes architecture allows for significant customization. Custom schedulers can be deployed to work alongside the default Kubernetes scheduler or to replace it entirely. API servers can be extended with custom resource definitions and API aggregation. Cloud providers can integrate deeply with Kubernetes using the Cloud Control Manager. The flexibility of Kubernetes architecture allows organizations to tailor their clusters to specific needs, balancing factors such as operational complexity, performance, and management overhead. Okay, so yeah, there we are. Just a deeper look at what the components are. Okay, and yeah, I think this has been worth it. So if you're enjoying this, share this with people in your community and let's learn together. Meet you tomorrow with the next topic, okay, as we learn Kubernetes. Okay, so this is like laying up a ground, can I call it a good foundation, okay, for us as we start the Kubernetes. And I'm not a fan of jumping all over the area, okay. Even if it took me 1 week to study this, okay, I would read and study this for 1 week, okay. So have the same mentality that even if something sounds complex, we can read it and practice until we become very good at this. And I know as we study this, some of these components are going to be repeated over and over again, okay. They're repeated over and over again until we understand them. So yeah, thank you for learning with me. Talk to you soon.